Hello everybody, welcome to section 3.4 on the Fundamental Theorem of Algebra. So what I'm looking to do right here is to say that by the time you finish what we're doing here in this section, we're not doing too many things that we didn't do in section 3.3, except we're adding a few little notes about some fundamental theorems, some ideas, some concepts that will make life a little bit easier right here. So we're going to be able to find zeros and linear factors of polynomial functions as we did before, but with the added justification that we're given by the Fundamental Theorem of Algebra. And we should be able to use a conjugate pair theorem of zeros to find the zeros of a polynomial given a complex number zero. I know that sounds like a strange thing, but first things first, let's see if we can explain a little bit about what's going on with these expressions right here. And the first one I want to take on is this fundamental theorem of algebra. What does it say? Well, this is the statement in your book. It says if a p is a polynomial function of degree n greater than or equal to 1 with complex coefficients, then p has at least one complex zero. And you might look at that and think to yourself, okay, yeah, so well, yes, it doesn't seem like it says a whole lot right here. However, what the fundamental theorem does is imply that if we have a polynomial p of x and its degree is greater than or equal to 1, so that means a second degree, first degree, second degree, third degree, and so on polynomial, then what can we say? Well, if p of x is a polynomial, and let's just say that for argument's sake, we don't know what that zero is, but we're able to find one zero. So let's say p of x is an nth degree polynomial. Then we know that we can get at least one factor out of that polynomial, right? So let's say c, that's our zero, and we know that we can take that, if it's a factor, and multiply it by the reduced polynomial q of x. And you think to yourself, well, okay, yeah, if I can find a factor, I can write it in factored form. But here's the thing, q of x also is a polynomial with complex coefficients and quite probably a degree greater than or equal to 1. What could we say about it? Well, it can be factored too. So what's the implication? Well, while you're thinking about that, let's take a look at this second expression right here. What does it say? It says, okay, the linear factor theorem says if p of x is a polynomial function of degree n greater than 1, so this is just like our last one, with a leading coefficient a sub n that is not equal to 0, then p has exactly n linear factors. Well, think about what's happening right here. If q of x factors, that means q of x might have another factor that we can reduce out, right? So in other words, p of x could be factored yet again into another set of factors. So we'll call this x minus c1. We might be able to find another factor, x minus c2, times the reduced polynomial for that one. We'll call it q2 of x, right? And we could keep doing this again. More factors, right? And however many times we can factor that polynomial right there, q of x, q1 of x, q2 of x, and so on, we can continue to get factors. And so what this says is that if we have an nth degree polynomial, then we will be able to find n linear factors. Whoa. Yes, that seems like well, shouldn't be so big a surprise. Why do we need to go to all this trouble to try and state this? Let's look at it. If I've got a polynomial that can be factored, it says that, well, the possibility is that, for example, if I told you I had a polynomial, and we've done this one before, like p of x is equal to x to the fourth minus 16, what could we do? Well, we know that this guy factors as x squared minus 4 and x squared plus 4. And that furthermore, if we break this down a little bit further, right, we know that we're going to get x minus 2 times x plus 2 from our factor x squared minus 4. And we're going to get x minus 2i times x plus 2i. And so what our linear factor has to say about that is that, well, this is exactly what we would expect to happen. We have a degree n of 4, and we have, lo and behold, 4 linear factors with complex zeros. Right? And if we had any repeating factors, we might count those as well. Okay? So the conclusion right here is this third thing that they state. They say, all right, if we take the number of zeros of a polynomial function, if p has a degree n greater than or equal to 1, and p has exactly n complex zeros, provided each zero is counted according to its multiplicity, right? P is a polynomial of degree n greater than 1, then, this should say, then p has exactly n complex zeros. Fourth degree, 4 zeros. 2 of them are complex, but actually they're all complex, right? If you think about it, every real number is also a kind of complex number. All right, so I've done explaining the basic theorem right here. Let's put it to the test here in the next video.